So the solution to the problem in the Hong Kong building was to go along with a large number of pappers and to actually fit them to the vertical stack until the problem went away. A good engineering solution. In other words, you've used the theory to design your product, but you've then gone along on site and actually fixed it. Now, what that looks like is, there we are. There is a multiple 2 pappers, and behind we've got 3, another 3 over here on a different stack. The papper for production purposes, we decided we would make one size of unit, 4 liters, and that's it. So if you want to use more than one, you can either spread them up stack or you can put them in series. As a slight aside, when I designed this device, I was bearing in mind a comic strip from 1951 where our hero can't get the bad guys because his phaser isn't big enough, so he screws 2 together. Anyway, for those of you who are not science fiction fans, that is irrelevant. Now we have a possibility to actually control transients. For a very long time, we've had air admittance valves that control negative transients. The papper allows us to control positive transients. Therefore, we can address the problem of the sealed building. Now, our original concern in this area was driven by, we thought, of security-sensitive buildings, where you might not want to have too many roof-level openings. But in actual fact, the application that we've found for this is in a building with a flexible roof. This is the O2 Dome in the East End of London on the River Thames. It's now used as a venue for events. About 3 million people have used this in the last 2 or 3 years for rock concerts and all sorts of other devices. And what we've actually done is to use a combination of papper and air admittance valves and diversity to solve the problem of how to design a drainage system and retain taps in that building. Basically, we have some 6 accesses to the sewer system, so there is diversity of connection. So what we do is we connect all of the vent systems together so that we can vent quite happily and then put in a mixture of positive pressure transient devices and negative pressure transient devices to actually allow us to design that system without penetrating the roof structure, which was not allowed by the city authorities. So, based on that then, what we've been doing here so far is devising approaches to destroy pressure transients formed inside drainage systems. What I want to show you next and finish with is how we can actually use transients for a beneficial purpose. In other words, use exactly the same theory, but in reverse. We know that when last time I addressed IAPMO was in 2004, we had a meeting in Los Angeles. The main issue then was the SARS epidemic in Hong Kong. I think it galvanized a lot of the public health industry to actually take another look at the quality of our building drainage networks inside buildings and certainly the cross-contamination. The buildings, the Amoy Gardens building here in Hong Kong has the same sort of external drainage that we saw on the Pac Tin building, and we know that the cause of the contamination was dry traps here, and that dry trap, in actual fact, not very clear in this, is here just at the skirting board level of the bathroom. Now, with changes in floor cleansing, that trap is not going to get topped up with water because people don't use buckets and mops anymore. Right, so we can analyze what happened numerically using our models, and we can show that effectively we had an exchange of air between the space and the vertical stack that in actual fact with the fan moving sucked air out of the stack. When we have discharge down the stack, sucked air back into the stack, and so forth. So in other words, there was that space was effectively breathing the SARS virus, which was coming down the vertical stack here, because it's a highly diarrheal disease, and therefore the stack is a mist of diarrheal particles. Now, therefore, the problem is, how do we know if we have dry traps or not? Clearly, we can go around and look in all these traps, very labor-intensive and not at all useful. So that's not an option. So what we did was we came up with a proposal which was to use pressure transients to actually identify dry traps within a building. And to do this, we received a grant from the UK Engineering and Physical Sciences Research Council, which is the equivalent of your NSF in the States. And we also had industry and code body support from, as we can see here, from IAPMO and from people like BuroHappold, who are a firm of consultants in the UK. The CIBSE is a professional institution in the UK. SNIPEF, of course, Robert Burgoyne should have been here this week from SNIPEF as chairman of World Plumbing Council to introduce his work, and World Plumbing Council on the end here, and of course IAPMO, who actually also supported this project. Now, what we're going to show you is a non-invasive, non-destructive, remote testing technique for looking at whether or not you have dry traps. And you can ask the question, well, how are you going to do that? And really, it's quite straightforward. Because if you generate a pressure transient in a duct, then you will get, if you generate this pressure transient and you measure it round about here, you will get a positive pressure wave as that transient goes past. What happens next depends on the terminal condition. If the terminal condition is closed, you get a positive reflection of that transient, as we see here. If the end is open, you get a negative reflection. So if you knew what the system was like in its perfect state, and then you took a pressure trace, time pressure trace, with effectively a defective trap, an open end, you would know that you had a problem. And because you know the speed of the pressure wave is 320 meters a second, acoustic velocity in air, you know the time at which the reflection comes back, you know the speed, so therefore you know the distance. So in other words, if you like, it's a sonar system for drainage systems. It's exactly the same as you see in the movies when people say we've got a blip and somebody is 300 yards to port. That's exactly how it works.